Hello and welcome back. Glad you're still with us. We're on the 11th video here. This unit is equilibrium, and it is honestly short, but it is challenging. It's one of the harder things for most students to work through. There aren't many concepts, and it's all really about application. So, again, this video is aligned with New York State, the Chemistry Regents. It's giving you a broad overview of topics. It's not going into the finite details, although I may ramble into that. And I hope that it helps, refresh your brain. So let's talk equilibrium. Equilibrium is a reversible chemical reaction, right? You could take reactants and turn them into products. You could take products and turn them back into reactants. And this happens constantly with something that's at equilibrium. So they will be in equilibrium if two things are true. Equilibrium. Cool. Equilibrium. If the rate at which you go through the forward reaction is equal to the reverse reaction. So what I mean is that every time a reaction goes from reactant to product, at the exact same time a product turns back into a reactant. So it kind of would look like this. The reactants are on your left, the products are on your right. Every time a reaction goes this way, at the equal rate, something goes backwards. That's the first stipulation that you have to have. And if that's the case, if reactants go to products, at the same time products go to reactants, then the concentrations are constant. And this is a really big thing to try to kind of drill into your head, is that the rates are equal and the concentrations are constant. That is almost guaranteed in some way, shape, or form to show up on the Regents. Rates are equal and or concentrations are constant. That's equilibrium. It would be nice. That would be the shortest unit in the history of all of school if that was all this unit was about. But in chemistry, things get chaotic. Right? And we can change and we can alter the equilibrium and we can stress the equilibrium. And for this curriculum, we stress this in three ways: temperature, pressure, and volume. All right? Stressing the equilibrium is called the LeChatliers principle. And for most people, this is a very difficult concept. Okay? LeChatliers principle. Because what you have to do is take the information of shifting and equilibrium and combine it with the kinetic stuff that we talked in the last video about. And thinking about what this altering of equilibrium, if you can think about what that does to collisions, it will help kind of put your brain in the right place. So if we wanted to put it simply, which we will try to do, and then I'll explain a little bit when I use this equilibrium below us. But an increasing concentration, whatever you're increasing, whether it's a reactant or a product, what happens is we are creating more collisions. Just like we talked about in the last video. Okay, more collisions, faster rates. Now, what I mean by that is, like, let's say I increase the concentration of H2. Well, if I'm increasing the concentration of H2, right, there are more collisions with H2. Now, H2 happens to be a reactant. So I'm increasing the reactions on the reactant side. What do more collisions create? They would create more products. Right? So this would be what we would call a right shift. Because there are more collisions on the reactant side, that would make more products. It disrupts the equilibrium. The forward rate of the reaction is now happening faster than the reverse rate of the reaction. Shift to the right. Now, this is a exothermic reaction. Now, we're all thinking about the reagents here. So we know that we have a reference table, and in the reference table on table I, we could find this formula. We would see that it's exothermic. We could write energy on the product side. If you didn't know any of that, you could still use some basic knowledge. When a bond is formed, energy is released. This shows that bonds are being formed. H2 and I2 are coming together to make HI. We would be releasing energy in this process. Now, this has to be taken into consideration if we're going to change the temperature. So, increasing the temperature affects the word energy. Now, I'm not going technical here. I'm going example-wise. I'm using the example to explain what I mean. But when I'm changing the temperature, what I'm doing is I'm changing this. And just like we did on the H2 side of it, we're going to think about this part of the equation being changed when I change it. So let's say for this, I'm going to use a harder one, a harder example. And I'm going to say, what would happen if the energy or if the temperature was decreased? Right? So if I took the energy away from the product side, what would happen? Well, the real scientific fact of what would happen is there would not be energy for HI to absorb to create a reverse reaction. This couldn't happen. If energy was removed, you could not make the reverse reaction happen. There is no energy for HI to absorb to break apart. And so as a result of this particular example, the equilibrium would again shift to the right. And it would make energy, right? Like the energy would then increase as I am creating more products. Everything in LeChatliers is cause and effect. I did this. What does the equilibrium do in response? So in this example, I remove energy. The forward reaction is now continuing at the same rate that it was. It's just that it's continuing and the reverse isn't. So I've disrupted equilibrium. Now, as the equilibrium is shifting to the right, creating more HI, it's also creating more energy. Cause and effect, right? I removed the energy. The resulting effect is I recreated the energy. I replaced it with the reactants that I had. And the last thing that we can affect here is pressure. Now, pressure is something that only affects moles of gas. So if I am dealing with no gases, with an equilibrium that has no gases, there is going to be no effect on my equilibrium. However, in this case, I am dealing with gases. Sorry, that was being a little pain in the butt. So we are dealing with gases. I know that, right? Gas, gas, gas. Now, this is not a great example, but I have a total of 2 moles of gas on the right and 2 moles of gas on the left. Right and left both have 2 moles. So actually, pressure would have no effect on this equilibrium. But let's just change it for the sake of this example. And you're going to have to ignore my violation of the law of conservation of mass. But let's just say instead of 1 mole of H2, we were actually starting with 2 moles of H2. Now this would change the starting moles to 3. All right, so now if there was a discrepancy in the moles of gas, pressure would affect this. And let's just say we increase the pressure, meaning we're pushing molecules together. Well, if we're pushing molecules together, we already know that more collisions would occur and more collisions would lead to an increased rate of reaction. But what happens is when you have more pressure, you have less volume. Everything gets squeezed together. And in this case, we're trying to look and say, all right, well, if I had less space in a system, what side would the equilibrium favor? And the answer is it's going to favor the side that has less moles. There's a lot that you have to decipher to do that. You have to think about pressure and say what would happen to volume. And once you know what would happen to volume, you favor the side that matches it. Less volume favors the side with less moles. More volume favors the side with more moles. So again, in this case, with this made-up thing that I just put on the board, this would result in a right shift. Awesome. The last thing that we need to just discuss is a definition or a term. And the universe is crazy. The universe is chaotic. So systems in nature, meaning the universe, tend to proceed towards higher entropy and lower enthalpy. That's not a word we use much as far as actual definition is concerned. This is another way of saying heat energy. So systems in nature are always trying to proceed towards higher amounts of entropy and lower amounts of energy. The universe is random, and it uses the least amount of energy that it can to achieve random configurations. Okay, higher entropy and lower energy. I hope this video really helped at least refresh some of the things. This is one of those units that you're really going to need to practice. This is not one that you can kind of watch and say, all right, yeah, I remember all of this. You really should go practice some LeChatliers, understanding shifts and collisions, and equilibrium, concentrations are constant, rates are equal, all of those things. Even though this unit is short, it can be very challenging. So, thank you for watching. Please hit the like button, subscribe to the channel, help me out. That would be greatly appreciated. The more people that we can get to understand chemistry, the better the future has for all of us. Thank you so much. I will catch you in the next video where we're going to be talking about redox, another one that most people really don't enjoy. So, thank you very much, and I will see you soon.